Hi guys, so we're going to talk about equilibrium and the equilibrium constant, KEQ, today. So first we have to define equilibrium. And so equilibrium is a state of rate balance between two opposing changes. And so we've talked about forward and reverse reactions, and that's what equilibrium is referring to. It's saying that the rate of the forward reaction is equal to the rate of the reverse reaction. And so RxN, that's just an abbreviation for reaction. And so most reactions are actually reversible. What you might see most of the time is we define a forward reaction, that's what we put on paper. So for example, if we have A plus B reactants go to C plus D, products plus energy, this is our forward reaction, which is exothermic. If we reverse it, then we get that what used to be our products are now our reactants, C and D, plus energy, making this endothermic, make A and B. And so this is our reverse reaction. And so how we represent a reaction that has forward and reverse capabilities is like this. So we still have one way kind of defined as the forward, which would be A plus B goes to C plus D. But notice what's different. Instead of using our traditional arrow, we have a double arrow. And so this is to state that both reactions are occurring simultaneously. So both are happening at the same time. They're kind of competing in a sense. And so using an example that we've seen a lot, the Haber process, which is making ammonia, we define our forward as adding nitrogen gas plus hydrogen gas to make ammonia, and that has some amount of energy associated with it. This actually has a reverse reaction too. So as we are making ammonia, ammonia is simultaneously breaking down into its basic building blocks of nitrogen and hydrogen again. And so using that idea of how we represent it just with our double arrow. And so I put a couple memes here because this is kind of a weird thing to visualize. How can one thing be making a product that is simultaneously breaking down at the same time? I just realized this is a typo. This says NH2 on your paper. This should be NH3. So my memes here, for example, the one on the left here, girl, you can't win, because notice how she is walking up a down escalator. Both her movement and the escalator's movement are happening at the same time. If they're equal, if they're happening at the same rate, so she is walking up at the same rate that the escalator is going down, she will stay in the same spot on the escalator. It'll look as if nothing is changing. So, the best thing about learning about equilibrium is that nothing changes. At least that's what it appears to our eyes. So, even though it looks like things aren't changing, those rates, those reactions are actually happening. So, let's go over some properties here. And so, as I just said, equilibrium is dynamic. And all this means is that it's in constant motion. Equilibrium only happens if you have what's called a closed system. And so the difference there is closed is some sort of controlled container, right? If you just have a reaction that can go to equilibrium, open to your surroundings, the air, lots of different changes that can consistently be happening, that's not technically closed. So it only happens when it's closed. And what's really cool about that is if it is a closed system, it will remain that way forever. So it will forever be changing and reacting, but yet at the same time, nothing changes. So the amounts of the products and reactants will be constant, but the rates are the same. So that's this last thing here. So you have different concentrations, but the rates are equal. And so just because the rates are equal doesn't mean our concentrations have to be. So really what our equilibrium constant is going to be kind of a ratio of how much product we can make. And so we'll get into that here on the next page. So different types of equilibrium can occur. The main one we're going to talk about is chemical. And so again, reminding ourselves the rate of the forward reaction is equal to the rate of the reverse reaction. Bringing back the Haber process, yes, it produces ammonia or NH3, but the ammonia is decomposing back into nitrogen and hydrogen. So you're thinking, okay, if this is such an important reaction, it just breaks down. Why do we use it? How is this even productive? But we're going to talk about in a second here about how we can force it to act the way that we want. But before we get there, let's talk about this equilibrium constant. And so this is defined as the ratio of amount of product to the amount of reactant. So we call this our equilibrium constant. So again, even though both reactions are happening, we are going to be able to reach some point of constant concentrations because of our rates being equal. And so again, this KEQ, that's what we're talking about here, capital K, little eq, is the number that represents how far the reaction went. So how much product were we able to make before the rates became equivalent? And so we just write it as the concentration of products. So bringing back those ideas of brackets representing concentration over the concentration of reactants. And so we have a more specific way to represent this, and it gets its own fancy term. And so we're going to define the mass action expression. And so the mass action expression is a ratio of concentration to products, but we also use the coefficients and use that ratio of moles of to each other. And so this is helpful to determine the degree to which the forward reaction proceeded. So how far was it able to? How does it change depending on the concentrations of each of its parts? And so the lowercase letters in this reaction here, those are going to be the coefficients. So we're just taking some generic reaction where capital A reactant with the coefficient little a added to capital B reactant with its coefficients little b is in a reversible process with C and D. And so how we express these is products over reactants. So we're saying, hey, the concentration of whatever capital C represents to the power of little c, and then that's going to be multiplied by your other product, capital D, to the coefficient of the lowercase one, all over concentration of A to power of little a, and then the concentration of B to the power of little b. So this is how you would write a mass action expression. And so reminding ourselves what's going on here is we always put products over reactants. Coefficients become exponents. And then the concentrations are being multiplied. So let's practice writing a mass action expression for this example here. So I start with writing KEQ is equal to, and then a division line, and then I'm going to write my product with its coefficient as the exponent. So SO3 gas to the second power, and then I'm going to put my reactants on the bottom over SO2 gas to the second power times O2 gas, which does not need a power as it's to the first. So that's it. That's just what it looks like. For the next one here, this is an example of a phase change, or sorry, not a phase change, a solution equilibrium, which we'll talk about here in a second too. But how we write this out, very similarly, set up that KEQ is equal to calcium plus 2 aqueous. So notice how I'm writing both the charge and its state of matter times chlorine minus 1 AQ to the second power all over calcium chloride solid. All right. Awesome. So we are going to move on and do an example where we can actually calculate the equilibrium constant. So if I had generic equation, A plus B goes to 2C plus energy, and we're given concentrations, it wants us to figure out what our equilibrium constant is. So the first part we have to do is write that mass action ratio. Our product is C to the second power, and that will be over concentration of A times the concentration of B. If we plug in our numbers, we get that 10 squared is all over 2 molar times 5 molar. So if we were to square everything on top, we get 100 molar squared all over 10 molar squared, giving us the equilibrium constant of just 10. So this being a ratio, totally cool that it does not have units. Don't expect these to have units. And so what this is telling us, this value of KEQ, is just how much products formed before we got to equilibrium. And so what you need to know is that the greater the value, the greater the concentration of product at the equilibrium. And so here's a little table that kind of like summarizes what's going on. So if you have a KEQ that's equal to 0, the reaction doesn't start at all. Nothing's happening. You didn't form any product. If you have it less than 1, your reaction goes a little way, but it's actually going more the reverse than the forward. If you have an equilibrium constant equal to 1, that means your products and reactants are equal. If it's more than 1, then your reaction is mostly going towards your products. And then if you get an infinite number, it must have gone all the way. And so the biggest thing here is, having kind of an idea that if this is a ratio, and so if thinking about, the generic here, I'm going to write this off to the side here. If KEQ is equal to products over reactants, if your products are large and your reactants, are normal or low, the larger the amount of product, the larger the KEQ. If these are equivalent, it would just like be saying 1 over 1, or your KEQ would be equal to 1. That's why your products and reactants would be equal. So as long as you kind of have the idea of how to use a fraction, you don't really have to memorize this. Just be able to reason through it. That very large KEQ is because you have a large product. If you have a really small number, that's because your reactants are really big and your product's not, right? And if you divide by a big number, this should be small. All right, And so another big thing is just making sure that we know how to order powers of 10, because most of the time our equilibrium constants are going to look like this. And so remembering what does it mean to have a negative power 10 versus positive, which one's bigger. And so what we're going to do is place these equilibrium constants in order from what goes the least far towards the furthest. So the furthest is going to be the largest. The least is going to be the smallest. And so ordering these, the largest value that I see is an actual positive exponent. So this would be our awesome in sense of finding our products or making products. And so since this is the, I'm going to label it here furthest, and then looking, the larger the negative exponent, the smaller it is. And technically, looking at the coefficients, 2.1 is smaller than 9.3. So this is actually going to be the least. And if that doesn't make sense, think about it in terms of, you know, if you're writing all the zeros out, something like this, and this might not be exactly -9, I'm just using it as an example. But since they're both the same power, it's easier to see with the coefficient that this 2.1 would be less than 9.3. And so if we have our furthest and least, it's not so hard to figure out the next order. So least would be first, then we would have D, A would be third, and then the furthest would be our fourth order there. All right, now for your other types of equilibrium, we have solution equilibrium. This is what happens when a solution is what we call saturated. And so if we have a ton of sodium chloride, like in this example, you're going to get to a point where you've already dissolved as much as you could in solution that some of it actually starts to precipitate out. And so again, it looks like this concentration wouldn't be changing. It looks like you have the same amount of little solid pieces of salt that haven't dissolved, but they're actually still moving. There's still some that are dissolving, and there's still some that's coming back into the solid, even though it looks like the same quantity. Then also we have phase or physical equilibrium. The rate of the forward phase change is equal to the reverse. So a good example of if we define water going from solid to liquid melting as the forward, the reverse of going solid to liquid would be going liquid to solid, so freezing. So we could say that melting is occurring at the same rate as freezing. And so this would happen at 0 degrees Celsius. So again, making solid water out of liquid, making liquid water out of solid, both of those changes are happening, but since they're equal, it doesn't look like much is changing. All right, so that is it for 9.2. 9.3 is really short, so we'll just zip through that here. And so this is Le Chatelier's principle. Excuse my French accent, I'm not very good at that. But pretty much why this is important, because you don't always want your system to be at equilibrium. Like we were just talking about the Haber process about making ammonia, and because the ammonia breaks back down into nitrogen and hydrogen, you don't want it to do that. This is an industrial process. We want to make as much product as we can, and so we make the equilibrium work for us. So the definition is that if we have some sort of system at equilibrium and we subject it to a stress, the equilibrium shifts to relieve the stress. All right? And so what we define as a forward shift is going towards making more products. A reverse shift is going towards making more reactants. And so these are all different stresses we can add. And it's pretty much just like reaction manipulations we can do. And so you could go and read through this table, but I think it makes more sense to think about it in the way of a teeter-totter. And I know that sounds ridiculous, but I'll show you with these examples here. So I'm going to give you an equation and say, what happens if we increase the temp? What happens if we change the concentration or, pressure? And so the way I want you guys to think about this is think about our reaction as if it was on a teeter-totter. And we are going to place or I guess I'm going to change the fulcrum to the double arrows here. And we're going to pretend like we have a ball that's sitting on our teeter-totter. And whatever way the ball ends up rolling is the way that our reaction shifts. And so that's part of it. But the other thing is figuring out where do we add or increase things. So if we're increasing the temp, if you see temp, this has to do with the energy term. And so if we increase the temp, that means we are going to push up, increase this energy term here, which in turn would make our teeter-totter go at an angle as such. Now, what's going to happen is our ball is going to end up rolling this way. And so what we're going to say happens is it shifts right. We end up making more product. And thinking about that, think about what we did is if this reaction takes energy, it's endothermic, you need heat for this to happen. If we add heat, this is getting more sufficient energy to have collisions and everything that we talked about in the beginning of what affects kinetics. And so increasing something on the reactant sides in turn is going to have to increase on the products. So again, the whole idea of this Le Chatelier's is that if we add a stress on one side, it will equal itself out. For this next one here, what happens if we increase the nitrate solution? So, again, thinking about this as a way it could shift on a teeter-totter, if we had a little ball sitting here, if we increase the nitrate, then we'll push up on this side. This would be our new teeter-totter, and the ball would roll this direction. And so what you're going to see happen then is this will shift left. So again, thinking about this logically, if you increase one side, you're going to shift the other direction and increase this side as well. Because thinking about it even as a math equation, if you had, x is equal to y, if you increase x, you're going to have to increase y, or vice versa. If you lose some of x, then you'll lose some of y in order to keep this equality relevant, in order to keep this being true. And so that's kind of what's going on here, except with chemical reactions. All right, so make sure to read through this table. If you have any questions, please let me know. And yeah, woohoo!